Okay? So those are the kinds of things we'll do. This, by the way, is called model free, and this is called model based. Okay? And we will try, one of the things I hope we will get in this class, by the end of these two classes, today's class and next class, is to understand at a deep level the difference between model free versus model based, and why both are needed in different problems. Okay? And we will give examples where we actually ourselves do model free and model based learning in real life, just so that we will get that distinction. Okay. So so this is basically the main thing that we're going to do in the next two classes, especially these seminars. Okay. But in doing so, we consider, again, this is basically the model based versus model based. I will actually let me look at that first, which is, in the case of model based, you will learn the action models, basically transition probabilities. A model of an action in an atomic sense is, if I were to do this action in this state, what will happen to me? Okay? If you have the model, you can simulate the world in your head. If you have the model, you can simulate the world in your head. The nicest thing about simulating the world in your head is nobody dies when simulating stuff in their head, except maybe in Inception, which if you have seen. Nobody dies during dreams. If you die in dreams, you can still wake up. Right? And similarly, if you're thinking about, okay, I can do this, then I can do this, oh, and then I'll die, oh, I won't go that way, I can do this, I can do that, I can go this way. This is what search is all about. Search is mental simulation, being done in a clean, algorithmic fashion. So if you have a model of the world, then you can simulate the world. That's very important. You can mentally simulate the world. And then, of course, from that, you can also learn the optimal policy and figure out what's the optimal action. But if all you wanted to do the optimal action, then you can also do model free, which is in some sense a cheaper technique because it cuts the middle thing out. The model is not learned. It goes directly from the problem specification to, I will do this if I'm in this place. It's kind of a reflex agent. Remember from the agent types, reflex agent doesn't think. It knows that if I'm in this state, I should do this action. And Q-learning basically is your best way of bankrolling reflex agents. You can learn with reflex agents, by doing Q-learning. Okay? And we'll talk about, as I said, Q-learning is sort of computing value, except you're remembering the Q values rather than just a single value for the state. So the crucial difference you want to keep in mind, as I said, is the ability to mentally simulate the future. If you ever need to mentally simulate the future, you need model-based learning. If you don't need to mentally simulate the future, then you can get by model-free learning. Okay? An example, I don't know why I said Iraq invasion. This must have been written during the time when we were invading Iraq, but whatever new country that we are about to invade, let's put that there. Swimming versus the country that we want to invade. Okay? You don't try to invade and see what happens. Although we seem to have done a couple of times that. Right? We actually plan. We have models, may not be greatest models, but we have models. We'll use that models to simulate, this is what we will do, this is the kind of strategy we will do. Warfare is the ultimate game theory. You do realize that the game theory developed in RAND Corporation out in Santa Monica. And it was basically bankrolled by DARPA, which is the progenitor of DARPA, which is US military. Warfare is the ultimate game theory. You guys, for example, know that Normandy invasion, there was huge subterfuge. They did humongous amount of stuff to make the other guys think that the invasion will be somewhere else. So they got all their people out there, and then you went here. You also knew, or if you don't, you're now knowing now, that Enigma code was broken way before. And they made a deliberate choice not to let Germany know. Turing basically broke Enigma code. You know that. They made a deliberate choice not to do anything that will let Germany know that they have broken the code. Which involved, for example, knowing that this particular ship containing some of you is going, and it's going to be torpedoed, it says, sorry, it's for the greater good. You guys will be gone, but the rest of us will be around. Seriously, this is what basically warfare is. You essentially let a few people go just so that Nazis won't know that we broke Enigma. And then much later, of course, you're waiting for the big payoff. Do you see what I'm saying? So, now the point is, we do simulations, mental simulations, humongous mental simulations for things like war. Versus swimming. Swimming, you just do it. It's a Nike. In fact, by the way, Nike is the model-free capital of the world. Right? It just says, just do it. Don't think, just do it. Right? So, swimming, there is no point in thinking. So suppose I want to swim, I'll do this, do this. In fact, one of my students told me that I can simulate my swimming by lying on the floor. First of all, that's a poor simulator. That poor guy might sink. But secondly, that's still simulating in the external world. It's a poor simulator. It's not a mental simulator. We're extremely bad at mentally simulating swimming. Because there's no models. Remember long back I said, I think it looks long back, but when this course started, I said, when Coursera started, I was worried that I won't have a job, and that I was going to become a swimming instructor. Why? Because swimming can't be learned from videos and reading books. Except, I guess, the one or two people who apparently can do that. Right? For most of us, somebody has to hold us and sort of show how, and then in fact, you need to figure out what is happening when you're doing swimming. In fact, in a world where we have simulators for flights, we don't have swimming simulators. Swimming simulators are called swimming pools. If you don't want to get wet like my student, just hanging around on the lab floor is not going to help. It's a very poor simulator. So in swimming, thankfully, you may have higher level planning as to, okay, I will go from here to here, swim from here to here, then from there to there, there to there. And then the actual parts of what I'm going to do at various points, I'm not going to plan this out. I'll just do it Nike way. And what I have learned, I mean, you can call it muscle memory or whatever the heck you want to call it, but that's model-free learning. What's the difference between just do it? You, who never swam, was just do it, the swimming champion. Neither of you can actually simulate very well, or even reasonably, what happens when you do various things. But you have much more experience because of which you have a good model-free Q values, essentially. So at that point, you know exactly what's the right action to do, reflexively. Okay? Keep that in mind. So by the way, one other thing is one of the crazy things that people tend to think of, including these OpenAI people as well as the AlphaGo people, is that somehow you're learning stuff from nowhere. It's all being done with no knowledge. So how many people believe that AlphaGo learned how to play chess with no knowledge about chess? How many people think that it played how to do Go without any knowledge of Go? Neither of them are true. It had a simulator. Somebody built the simulator. Rather than tell, the AlphaGo people, these are the actions, these are the effects, etc., they gave a piece of code. Somebody else wrote it. Tell me when DeepMind writes that code also. It actually comes up with interesting games, and just learns how to play it and also seduces you guys to play it so that you will be very impressed that it won. How many of you, for example, know that we achieved quantum supremacy? Do you care about the problem that was solved to reach quantum supremacy? You should all go read that. It's a made-up problem, just to prove a point. Nobody really ever wanted to solve that problem. People didn't even know that problem existed. But it's a problem that they were able to solve to show that quantum computers, in this particular case, definitely do better than classical computers. It's the same thing that will happen if you were to make games by yourself and start playing in a computer sense, because nobody else might be interested in playing that game. The ones that we play, we have essentially given the simulator. That's knowledge about the game. So anytime somebody says, I don't need any knowledge whatsoever, and they say, I just need a simulator, I say, stop. Who gave you the simulator? You don't want to hear me, you want just the code. Somebody has to write the code. Okay? So simulator is a way of actually telling about the world. If on the other hand you directly walk in the world that we all live in, and then you fall down and you get up, etc., then that's great. You know where reinforcement learning is, if you hear that reinforcement learning is being used in a following application, you should all run for the hills. What is this application? It's a very popular application. If you hear that reinforcement learning being used for AlphaGo, you don't have to run for the hills. I mean for Go, okay? If you're using reinforcement learning for some other application that we all think about, you should run for the hills. Which one? Huh? Social media, who cares? What? Yeah, kind of, I knew it, but I wouldn't all run for the hills. What? What other things are you guys enamored with about AI? What? Google Waymo. Imagine it's doing true reinforcement learning. True one. They'll run over a few people. Oh, looks like it's not good. even though those screams sounded kind of good when they were going under the car, apparently people don't like it. You see what I mean? That's what reinforcement learning is. True reinforcement learning with no knowledge. Okay, so in fact, people, I think Jan LeCun has this little video that he keeps showing that if you're learning by video, self-driving by video, this thing, then essentially I wanted to put that animated GIF. It's car turning over a steep road, falling off. Gets up, goes on the steep road again, falls off. Would you want to be in that car? Even Google doesn't have that kind of a money to have huge number of cars dying. And certainly we don't have any money to die, even though Tempe did allow somebody to die, as you guys know, with the stupid Uber self-driving car, which is worse than normal car. But anyway, so keep all this stuff in mind. If you are using a simulator, you're using somebody's knowledge. And in fact, if you don't use a simulator, then you have to really work in the world, and that's very costly. That's very, very costly. Many interesting domains like self-driving, trying it out in the real world is no good. I mean, they can say, look, unlike humans where you become a good driver, your friend doesn't become a good driver. Whereas if one Google car becomes a good driver, all Google cars become a good driver. So, Larry and Sergey can come and say, come on guys, Tempe, enough people. A few will die. It's for the greater good. It's like that Enigma thing, some people going on the ships got torpedoed. We knew they were going to be torpedoed, but we kept our mouth shut. We can do this, Tempe, I would say Idaho, but maybe they're mostly coming to Tempe these days. And so that way you could argue, but obviously we don't like that at all, because cost of failure is extremely high, and that's worthwhile to keep in mind. By the way, so actually it's kind of useful to keep this thing which has nothing to do with actions, but it gives an interesting distinction between, actually before going here, I forgot to say this part. Passive versus active. Passive versus active, really Active reinforcement learning is the only thing that you're interested in, which is the agent trying to figure out what action it should make when it finds itself in any state, which is what MDP optimal policy is. However, on the way to it, we will, just like in the case of MDPs, we wanted only how to compute optimal policy. But we went through the intermediate step of, if somebody were to give me a policy, how do I compute its value? And I used that to kind of understand how to do the optimal policy. One case will be just a set of linear equations, the other case there's a max. Remember the Bellman update. Okay, so in reinforcement learning too, we distinguish between passive versus active learning. In the case of passive learning, the policy has already been decided. And you're just blindly following that policy. You can't change the policy. But you can learn to have this, what do they call the impending doom or impending good experience. You can see that in a minute things are going to get bad, or in a minute things are going to get very good. Because I've tried this policy multiple times and this is what is going to happen. So an example of that, I don't think I have it here, in the next slide it shows up. When you were a kid, you sat in the back seat, tied to the seat, and your parents were taking you, they are controlling the policy. And even now for your dogs, that's what happens. The dog is in the car, and you are controlling the policy, unless your dog drives. But when you were a kid, as you turned and you went towards a place where you have seen the last 15 times this ice cream parlor, and then you have these memories of nice sweet ice cream that you get to eat, you start jumping up and down. You realize that this is going to happen. Your dog does too, not for ice cream. It basically starts doing it for vets. Dogs have essentially the ability, the sixth sense, to figure out that they're being taken to the vet's office. Were they born with vet gene or something? No. They have learned it after a while that no good ever comes when you go to the vet's office. They seem to poke you. And so the moment you turn this way, oh my God, I don't like this one bit. That's learning. It's unfortunately sad learning. It's learning that doesn't change anything. But at least you know, oh yeah, I know I'm going to have some really bad time right now. Do you see what I'm saying? That's passive learning. And it's useful sometimes, basically, to understand that you essentially are able to predict what's going to happen to you in future, even though you can't change your future. That's passive learning. In the active learning, you're essentially trying to figure out what's the actions I should do such that I'll get the best future I can get. Okay, that's the distinction. And we will start with passive learning because that's sort of connected to policy learning, policy evaluation, and then go to active learning. Okay. Actually, let me skip over this for now and then actually do the passive learning. So here's the simplified task. So I have my MDP picture here, okay? And again, I don't know the transitions, I don't know the rewards, I'm just given a policy pi because it's passive, so some particular policy has been given. So this is the policy I've been given. Those arrows telling me which action to do in what state. Okay, so this is the policy that I know is going to happen. So my question then is, can I learn the values of these states? I know the rewards because the moment I go to that state, I know the reward. And next time I go to the state, I'll get the same reward. The question is, can I get the value? So for example, as I was saying, when you were a kid, your policy was mostly dictated by your parents. If it's 6 a.m., wake up and go to school. If you however, did learn to detest Mondays and look forward to Fridays. You didn't control your life, but you learned that, okay, this is going to be a bad day for me. It's Monday. Okay, and that's what is passive learning. Okay. So one simplest way of doing passive learning is the following, which is, in this particular case, I will start from, let's say, any place, take take the action that the policy is asking me, figure out where I go, take the action, what I'm supposed to do there, etc., until I die. In this case, actually, I stop, each episode stops with a termination state. Okay, the square ones are termination states. It turns out actually that this thing can also work for non-terminal states and with discounted rewards. But we'll just understand the simpler case where terminal states and undiscounted rewards. Okay? So here is a possible episode. Just make sure that you understand that. I'm in 1, 1, I went up. Because I'm in 1, 1, I got a -1 reward, because the expectation is that rewards is -1 everywhere except here and here. This is +100 and -100. So instead of -0.04, it's -1 here for every state. So then I did this up, and it's the same kind of actions. When I try to go up, I go up with 0.8 probability and sideways with 0.2 probability. Okay? So then I went up this time with high probability, I basically went up here. Those are probabilities. You don't know this. Remember that. Okay, I just told you the word probabilities, but you don't know this. This is the world I made. I am controlling this world. I am the God. You're only acting in this world. You're in fact not even acting in the world. You're seeing your parents act in this world. Okay? So all you know is you did 1, 1 and you were in 1, 1, you did up, you got 2, 1, 2. And in 1, 2 you're supposed to again go up. You did that. It so happened that you just stuck in 1, 2, even though you tried to go up, because you didn't know why. But I'm telling you, unbeknownst to you, I made these actions stochastic, and when you try to go one way, you go with 1.2 probability, you try to go the other directions. And in this particular case, in both sides there are walls, and so you wind up staying in the same state. This is the gods knowing what's happening to you. But you don't know all of this stuff. You just getting the experience. Okay? Then 1, 2 minus 1, 3, etc. You know. Any questions on how an experience like this can be made? And then another experience. If I have these two experiences, the question is, can I just compute the value of a state? What is the value of a state? Value is the expected cumulative reward from that state, according to this episode. Okay? So what happens is, in the U of 1, 1, if you are in U of 1, 1, then basically you add up all these rewards, you will get 92. The same way you add up all these rewards, you get 100 minus 106. So one time I got a 92 cumulative reward, the other time I got a minus 106 cumulative reward. So what's my best guess as to what is the cumulative reward, expected cumulative reward I will get? Average of those two. Okay, so that's it. U of 1, 1 is minus plus 92 plus minus 106 by 2, which is minus 7. And similarly, one of the other things you can do is, you can also see what happens for 3, 3. 3, 3 occurs here as well as here. So you can use the same experience to compute the values of the other states. You don't have to start from there separately. So from 3, 3, I have minus 1, minus 1, minus 1. So minus 3 plus 100. Okay, that is the plus 97. Okay, actually there are 2 3 3s here. Did you guys notice? Right. So because of which 1 3 3 is 99, other 3 3 is 97 until you die, and the other 3 3 here is minus 102. I add all of them, subtract or divide by 3, 31.3. Success. You learned a reinforcement learning algorithm. Impressed? This is a reinforcement learning algorithm. You add numbers, divide. It doesn't get any better. You sometimes also multiply by alpha. The question is not that reinforcement learning algorithms are, when you look at the algorithm, it's very underwhelming. It doesn't look like, is this what happens? My God, I expected something like AVL tree balancing. at least 8 pages of code. Otherwise what's the point? I'm doing computer science for crying out loud. What happens in reinforcement learning is essentially you're trying to look at each experience and you're quickly trying to improve your estimates. It's just estimate improving. What's interesting is there are better and worse ways of estimate improving. And much of the distinction between the reinforcement learning algorithms is to understand that this is like the stupidest way of doing it. This is called the Monte Carlo estimation, or what's called the direct estimation. It will work. Okay? And it's like a small piece of code, and you keep doing enough number of things, and as you behave, after a while you will get the actual values. And the values would be as if the guard computed policy evaluation using the Bellman equations. Why? Because the guard, that is who am controlling the world, I essentially have the actual stochastic distribution for each of these actions. But the point of probabilities is that in long term, the ratio of the number of times an outcome occurs with respect to another outcome is proportional to their probabilities. The more probable outcomes occur more often. The less probable outcomes occur less often. That's a law of large numbers. If I tell you that this is going to come 0.9 heads, 0.1 tails, and I'm about to toss, can you guess whether it comes heads or tails perfectly? No. But if I were to tell you that it's going to come 0.9 heads, 0.1 tails, I'm going to now toss this 1,000,000 times. Can you start putting bounds? You have much better idea then. 900,000 approximately versus 100,000 approximately will be the number of heads and number of tails. That's the law of large numbers. That's what probabilities are for. So the world becomes its own simulator, essentially. And the probabilities will come in these summations that way. And so in essence, you are solving the policy evaluation by just simulation. Okay? It looks almost as if, why did you make us go through that other stuff if I can do this? Well, because you want to understand, and in fact the only way you can figure this out is try to take something like this, right? And try to compute the value of this policy knowing the model. See how much time it took. Try to compute the same value this way and see how many iterations you have to simulate and how much time it took. And remember, there are two kinds of complexities. One is how much time did you have to wait before the value stabilized. And secondly, every time you actually act in the world, you're taking a chance of dying. Okay? And the expectation is that if you had the model, you would have computed the policy value much faster than this way. Okay? So somewhere here is like, in terms of the cost, let's say, with the model, the cost for policy evaluation will be this, let's say. With this approach, it will be somewhere here. And the next approach I'm going to tell you will get you somewhere in between. Okay? And in fact, all reinforcement learning is in between these two, in essence. Okay? So now let's look at this direct estimation and see, you understood, everybody understood this, right? I'm just basically doing the simulation, and then just basically for each state I'm looking at how much actual, I'm looking at the problem as if it is a solution. The definition of the problem is value is the expected cumulative reward. So I took that directly and tried to compute reward for each sequence. I took the expectation, which is the average. You see what I'm saying? This, I would argue, is sort of like saying you took the problem specification of how to sort a sequence of numbers. A sorted sequence will have the following property, that if it's in the increasing order, then every number is smaller than the number to the right of it. Okay? And then you convert it directly into an algorithm, which is, I will generate n factorial permutations and check if any of them are sorted. That is a solution. That's actually a finite time solution. But the whole point of computer science is not to do it. Okay? So Monte Carlo is sort of like that. And you have to understand that. So what is it missing? What it is missing is it's acting as if each of the values in each of these states are independent variables. That's not true. In fact, the values of the states are connected to each other by the Bellman equations. Intuitively, if you are next to a neighbor who is very rich, you can't be very poor, where neighborhood is defined in terms of the actions. You see what I'm saying? But this guy won't realize that. He would essentially act as if there are S number of unconnected variables and it's estimating each of them separately. That's a huge, huge waste of time. Okay? So, let's say, oh, there are a bunch of things that happen here. So we are basically doing empirical policy evaluation, but we know this will be wasteful because it misses the correlation between the values of the neighboring states. So what do? We realize that they are connected by Bellman equations. Let's just use the Bellman equation. Yeah. But to use the Bellman equation, I need transition probabilities. You see what I'm saying? So what I will do is, first of all, the first thing is to just, this is an example to show that when you run on this particular little example, when I run Monte Carlo, at some point of time you might have things like this, where, for example, this one is +8, this is -2, this is +4, this is +1. That's globally inconsistent. Because how can this guy who's next to +4 be +8, whereas this guy who's next to +4 be -2? Given the same actions that they all have. That's what is not understanding the correlation between the values of the states. So to do that, what I'll do is I'll do Bellman equations, and the simplest case, let's see, where am I? Okay. The simplest case is I take the same example as before. Instead of estimating the values directly, I estimate transition probabilities. I can do that given the same thing, right? For example, if I am on 3-3 and I do right, what is the probability that I'll go to 4-3? Okay, that's one of the probabilities I need. So I'm in 3-3, I did right here. I'm in 3-3, I did right here. I'm in 3-3, I did right here.